Hello. I'd like to do just a brief video here on wavelength, and wave properties. We use this to explain several things in chemistry, and so I want to make sure you know how this works. Let me actually first of all change a pen color. First property I want to mention about waves, and here we have a wave. This would be the origin kind of going through here. Apologize, the line isn't real straight. Basically, one of the most important properties is the wavelength. That is the distance from basically two of the same points. You could do peak to peak or trough to trough. But basically that is abbreviated with a lambda. That's an upside down, looks like an upside down Y to most of my students. And again, that would be this here if you want to see it typed out. It is usually measured in meters. The other property that's very, very important is the number of times a wave goes up and down in 1 second. That's called the frequency, and that is abbreviated with the Greek letter nu. It actually looks like this. It looks basically like a V, and that is measured in either hertz. You'll sometimes see that written, and that's named after a person, or cycles per second. So sometimes you'll see that as s to the -1 because it's so many cycles per second. And again, that's basically just the number of times the wave will go up and down in 1 second. Now, one other thing which we'll mention here, we don't really focus on it a whole lot, is just the amplitude, and that's the distance from the origin up to the crest or down to the trough. Now, as far as these guys, what I want you to recognize is that there's a relationship between wavelength and frequency, and it is the product of the two things is equal to a constant all the time. This constant is the speed of light, and the speed of light is 3 times 10 to the 8th meters per second. Now that is the speed of light in a vacuum. As it goes through water or air or so forth, it does change, and that's why prisms work and so forth. But that is a constant. The key thing to recognize here is since the product of these two numbers is always the same number, as one goes up, the other goes down. So if you have a very long wavelength, a very high wavelength, you're going to have a low frequency, meaning it's going to go up and down fewer times per second. Now this is all can be looked at as part of the electromagnetic spectrum, and you'll see that here. And if you have real high frequencies, or real large frequencies, things like this, like 10 to the 4th times per second, that's rather low as far as up and down per second for a wavelength. You'll notice you have a very long wavelength, 1,000 meters. If we go to the opposite end of the spectrum, if you have a very, very high frequency, like 10 to the 20th, this wave is going up and down, 10 to the 20th times per second, the wavelength is very, very small, 10 to the -12th meters. You'll see this corresponds to the whole electromagnetic spectrum that goes kind of from gamma rays with your real short wavelengths through X-rays, UV, visible, infrared, microwaves, and radio waves being the longest. So these are your very long waves, these are your very short waves. And then the difference, of course, is related by this equation. Now we are visually able to kind of see this area here. The wavelengths that correspond from about 400 to 700 nanometers we can see with our eyes. We have chemicals and sensors in our eyes that allow us to see these. There are other wavelengths all around us. We just aren't sensitive to them. Your car radio is of course sensitive to the radio waves. X-rays will expose photographic film and so forth. But they're all here. But we can only see these. But that's just a small part of the overall spectrum. Now, one other thing you should be aware of is that each light travels in a wave. We describe it in a wave, but it has what's known as a wave-particle duality. You can also look at it as a bunch of photons of energy moving along. The energy of the photons is given to you according to the equation E equals h nu. E is the energy of a photon. Nu, of course, is the frequency. And h is something called Planck's constant. Planck's constant, and again this is always the same number, is 6.626 times 10 to the -34th joule seconds. So what happens is, remember, this is given to you in s to the -1 or cycles per second. So what's going to happen is your cycles will cancel and you're going to get the energy in joules. This will allow us to figure out a bunch of things, and I'll kind of show you some problems in a moment. Now the simplest type of problem you can do with this is I give you maybe the wavelength and ask for the frequency, or the frequency and ask for the wavelength. And it's fairly simple calculation. Let me show you how this works. If I know that C is equal to lambda nu, and let's take visible light. We were just talking about it. As I said, visible light goes from 400 nanometers up to about 700 nanometers, and that's an approximate. Okay, this would be your red light. This is going to be your violet light. If I said to you, what is the frequency of violet light, or for instance, so I'm basically asking you for this, and I'm giving you the wavelength in nanometers here, and we know this is a constant. Well, if C is equal to lambda nu, and I'm solving for nu, I divide both sides by lambda, and then this cancels, and so that my frequency is equal to C over lambda. Well, C we said is always the same number. It's 3.00 times 10 to the 8th meters per second. And of course, wavelength I said is 400 nanometers. Well, 400 nanometers is, a nano is 10 to the minus 9th meters. So I'll just write that like that. Now that's not in correct scientific notation, but that's okay. You'll notice your meters will cancel, and then you're going to get your frequency. And let me get out my calculator and do this for you. So I'm going to do 3 to the 8th divided by 400 to the minus 9th. And when I do that in my calculator, I get 7.5 times 10 to the 14th, and then this would be cycles per second. So if you could actually see violet light going along, what you would do is you would see it going up and down 7.5 times 10 to the 14th cycles per second. And if we come over here and look at this, that's about right. Notice 10 to the 15th is a little off the violet end. I'm just in the violet area, and I got an answer 10 to the 14th. So that answer actually makes some sense. Now that would be the simplest of the sorts of problems we could do, and it's just a very straightforward substitution. You know, this is a constant. I'd give you one of these and ask for the other, and then whatever one I give you, you basically divide from C to solve for the remaining one. So if I give you wavelength, you would simply divide both sides by that, so you do C over the wavelength, and that would give you your frequency, which is what we just did. If I gave you the frequency and asked for the wavelength, you would divide both sides by nu, and then that of course will give you your wavelength in meters. So you can go back and forth. Now with my honors students, I like to start combining these equations a little bit, and so let me show you how I might do this with one of my honors classes. So here's a sample question. A sodium vapor street lamp emits a bright yellow light with a wavelength of 589, which is in the yellow end of the visible spectrum. How much energy is emitted per mole of sodium atoms? Well, that's where I'm going to use this equation, that the energy of a photon is equal to h nu. And to do this, I'm going to need to plug in the nu, or frequency. But if you'll notice, I didn't give you frequency, I gave you the wavelength. But as I just said and just did over here, if you know the wavelength, you can solve for the frequency. The frequency would be the C over the wavelength. So if I divide this by this, I'll get my frequency, which I can then plug into here, which will of course give me the energy per photon. Now to get the total energy, since I'm told I have a mole of photons, I'd have to multiply this by 6.02 times 10 to the 23rd. So what I would do here is to get, first of all, get the frequency. I'm going to take 3 times 10 to the 8th, and again, C is always 3 times 10 to the 8th, and I'm going to divide that by my wavelength. Again, 589 nanometers. A nanometer is 10 to the minus 9th meters. So if I do that, I'm going to get my frequency, and I did this previously, and let me see what I got. I got 5.09 times 10 to the 14th. Okay, so that's the number of oscillations per second. That's how many times this will go up and down a second. And now what I'm going to do is take that, plug that into this equation, so there's my frequency. I'm going to multiply that by h, Planck's constant, 6.626 times 10 to the minus 34th, and I'll get the energy in one photon. So 6.626 times this number gives me the energy of my photon, and I again did that previously, and let me see what I got. I got 3.37 times 10 to the minus 19th, and that is in joules. So I now have my energy in joules, and so that would be the energy of one photon, but they tell me I have a mole of photons, so I of course now need to multiply this by 6.02 times 10 to the 23rd, and then when I do that whole process, I get 203,167 joules. Now if I'm going to round this, I'd really only be allowed 3 significant digits, so that'd be 203,000 joules or 203 kilojoules, depending on, some teachers might say, I want the answer in kilojoules or joules, and remember this relationship is 1 to 1,000. So that is one way you could kind of manipulate these equations to do a problem, where you're basically have to use one to solve for the other. And that would be kind of a simple way. Now let me show you kind of a more complex problem that we can do, and I've actually jumped ahead here and written some things out to make this a little bit easier. Now here's a very involved problem, and again, what ultimately we're getting to is the fact that we can use this equals h nu to compute the joules in a photon. If I then give you, say, a certain number of photons, you can figure out a total energy, and then we can go back to the energy calculations that we've done before, things like Q equals m delta T Cp and so forth, and then plug those into these sorts of equations. So this is very involved, which is part of the reason I jumped ahead, so I could write all this out and do this a little more quickly. What I do is I give you a mass of some gas with a specific heat. I know a lot of people like to have the Cp here, the little subscript, so we'll Cp 1.328 joules per gram degree C. You have these standard conditions. Here's the volume, and here's the number of photons. And the photons are given at this wavelength, and then they give you the pressure of the gas at a new condition, and they say, what is the new volume? Well, the first thing you need to do when looking at a problem like this is figure out, well, they're telling me I'm hitting this gas with a certain number of photons. I need to figure out, well, how much energy is being transferred. So again, I solve, the wavelength is given to me as 945 angstroms. That's 10 to the minus 10th meters. So that's 945 times 10 to the minus 10th. I then plug that into my nu is equal to C over lambda, which gives me the frequency, and then I can plug that into equals h nu and get the number of joules in one photon. The problem then tells me that there are this many photons, so I multiply them, and then this would be the total number of photons that is going into my gas. Well, what is that going to do to my gas? It's going to heat it up because I'm putting energy into it. Well, I can figure out how much that's going to change the temperature of the gas, which will allow me to figure out new pressures or volumes or whatever by using the equation Q is equal to m delta T Cp. This is my Q. This is how much heat, which is energy, that I'm transferring into the gas. My mass is given to me up here as 18.36, and my specific heat, of course, I just mentioned, is 1.328. Notice, by the way, anything given to me in the problem, I'm trying to highlight in blue so you know where those numbers come from. So this number actually came from here, and then I set this up, and I find out that my change in temperature is 138.8. If I know that my change in temperature is 138.8, I started at standard temperature, add this to 273, and then this number is my final temperature. Now there are two ways you can really solve this. One is P1 V1 over T1 is equal to P2 V2 over T2. I plug in my standard pressure and temperature and my initial volume of 15.24. I plug in my new conditions. Here's my new pressure that's, again, given to me in the problem. That's 1168. I'm solving for my new volume, and I have now figured out my new temperature based on the heat that I put into this gas as 411.8. You solve and you get a V2 of 14.96. You could also solve this using P equals nRT, rearrange that for V. My N would be my mass, 18.36, over my molar mass. Hydrogen cyanide is HCN, so that's 12 plus 14 plus 1 gives me 27. So if I take the mass over the molar mass, that'll give me my moles, or N. My pressure is in torr, so I'm going to use 62.4 for R. And my final T, again, we figured out is 411.8. So I can, once I get this temperature, I can use it in either problem. And then I'm going to divide that by my pressure. Again, my P2 given to me is 1168 in the problem. And I also get 14.96. So at this point, you could really do this in either way. But the key thing is, I'm hitting gas with some light. If I hit it with some sort of light, I can figure out how much energy I'm hitting it with, and then I can figure out the change in temperature. This is a common theme in my honors classes, so you'll see this in some of the problems, where when I apply energy or photons to something, I'm going to change its temperature because I'm putting in heat energy, and you can do these sorts of calculations. So I hope this helps you. Thank you.